Example 5, solve y double prime plus y equals sine x. Solution, the auxiliary equation is r squared plus 1 equals 0 with roots plus or minus I. So the solution of the complementary equation is y sub c of x equals c sub 1 cosine x plus c sub 2 sine x. Ordinarily, we would use the trial solution y sub p of x equals big A cosine x plus big B sine x, but we observe that it is a solution of the complementary equation, so instead we try y sub p of x equals big A x cosine x plus big B x sine x. Then y prime sub p of x equals big A cosine x minus big A x sine x plus big B sine x plus big B x cosine x. Y double prime sub p of x equals negative 2 big A sine x minus big A x cosine x plus 2 big B cosine x minus big B x sine x. Substitution in the differential equation gives y double prime sub p plus y sub p equals negative 2 big A sine x plus 2 big B cosine x equals sine x. So big A equals 1 negative 1 half, big B equals 0, and y sub p of x equals negative 1 half x cosine x. The general solution is y of x equals c sub 1 cosine x plus c sub 2 sine x minus 1 half x cosine x. We summarize the method of undetermined coefficients as follows. Summary of the method of undetermined coefficients. Number 1, if big G of x equals e to the power kx times big P of x, where big P is a polynomial of degree n, then try y sub p of x equals e to the power kx times big Q of x, where big Q of x is an nth degree polynomial whose coefficients are determined by substituting in the differential equation. Number 2, if big G of x equals e to the power kx times big P of x cosine mx, or big G of x equals e to the power kx times big P of x sine mx, where big P is an nth degree polynomial, then try y sub p of x equals e to the power kx times big Q of x cosine mx plus e to the power kx times big R of x sine mx, where big Q and big R are nth degree polynomials. Modification: if any term of y sub p is a solution of the complementary equation, multiply y sub p by x or by x squared if necessary. Sidebar: the graphs of 4 solutions of the differential equation in example 5 are shown in figure 4. Figure 4. Example 6. Determine the form of the trial solution for the differential equation y double prime minus 4y prime plus 13y equals e to the power 2x cosine 3x. Solution. Here, big G of x has the form of part 2 of the summary, where k equals 2, m equals 3, and big P of x equals 1. So at first glance, the form of the trial solution would be y sub p of x equals e to the power 2x open big A cosine 3x plus big B sine 3x close. But the auxiliary equation is r squared minus 4r plus 13 equals 0 with roots r equals 2 plus or minus 3I. So the solution of the complementary equation is y sub c of x equals e to the power 2x times open c sub 1 cosine 3x plus c sub 2 sine 3x close. This means that we have to multiply the suggested trial solution by x. So instead, we use y sub p of x equals x times e to the power 2x times open big A cosine 3x plus big B sine 3x close. The method of variation of parameters. Suppose we have already solved the homogeneous equation a y double prime plus b y prime plus c y equals 0 and written the solution as equation 4 y of x equals c sub 1 y sub 1 of x plus c sub 2 y sub 2 of x, where y sub 1 and y sub 2 are linearly independent solutions. Let's replace the constants or parameters c sub 1 and c sub 2 in equation 4 by arbitrary functions u sub u sub 1 of x and u sub 2 of x. We look for a particular solution of the non-homogeneous equation a y double prime plus b y prime plus c y equals big G of x of the form equation equation 5 y sub p of x equals u sub 1 of x y sub 1 of x plus u sub 2 of x y sub 2 of x. This method is called variation of parameters because we have varied the parameters c sub 1 and c sub 2 to make them functions. Differentiating equation 5, we get equation 6 y prime sub p equals open u prime sub 1 y sub 1 plus u prime sub 2 y sub 2 close plus open u sub 1 y prime sub 1 plus u sub 2 y prime sub 2 close. Since u sub 1 and u sub 2 are arbitrary functions, we can impose two conditions on them. One condition is that y sub p is a solution of the differential equation. We can choose the other condition so as to simplify our calculations. In view of the expression in equation 6, let's impose the condition that equation 7 u prime sub 1 y sub 1 plus u prime sub 2 y sub 2 equals 0. Then y double prime sub p equals u prime sub 1 y prime sub 1 plus u prime sub 2 y prime sub 2 plus u sub 1 y double prime sub 1 plus u sub 2 y double prime sub 2. Substituting in the differential equation, we get a open u prime sub 1 y prime sub 1 plus u prime sub 2 y prime sub 2 plus u sub 1 y double prime sub 1 plus u sub 2 y double prime sub 2 close plus b open u sub 1 y prime sub 1 plus u sub 2 y prime sub 2 close plus c open u sub 1 y sub 1 plus u sub 2 y sub 2 close equals big G. Or equation 8, u sub 1 open a y double prime sub 1 plus b y prime sub 1 plus c y sub 1 close plus u sub 2 open a y double prime sub 2 plus b y prime sub 2 plus c y sub 2 close plus a open u prime sub 1 y prime sub 1 plus u prime sub 2 y prime sub 2 close equals big G. But y sub 1 and y sub 2 are solutions of the complementary equation. So a y double prime sub 1 plus b y prime sub 1 plus c y sub 1 equals 0. And y and a y double prime sub 2 plus b y prime sub 2 plus c y sub 2 equals 0. And equation 8 simplifies to equation 9. A open u sub 1, equation 9a open u prime sub 1 y prime sub 1 plus u prime sub 2 y prime sub 2 close equals big G. Equations 7 and 9 form a system of two equations in the unknown functions u prime sub 1 and u prime sub 2. After solving this system, we may be able to integrate to find u sub 1 and u sub 2, and then the particular solution is given by equation 5.